So hello guys, welcome to this new video, and in this video we're basically going to discover the question that is reverse pairs. So in this question from LeetCode that is of hard difficulty level, we will basically be given an array and we'll have to return the number of reverse pairs that are present in the array. Now let's see what reverse pairs are. So they are basically a pair of two indexes. Like as you can see, it's given over here that they're a pair of two indexes i comma j such that I is less than j and both the indexes lie in the array itself, and the value of value that is present in the at the ith index, that is and nums of I, should be greater than 2 into nums of j. So like these are the two conditions, that is I less than j and nums of I should be greater than 2 into nums of j, that is double of nums of j. So this is the condition that we can establish a reverse pair. We can detect a reverse pair in the array given to us. Now let's see in this example given over here. As you can see in this array, this 3 comma 1 will be one reverse pair. Why? Because 3 is present at the index 3, 0, 1, 2, 3 and 1 is present at the index 4. So 3 is less than 4. If we take I as 3 and we take like j as 4, so 3 is less than 4. So the first condition is satisfied. Now we go to the second condition, that is nums of I, that is 3, should be greater than 2 into nums of j, that is 1. So 2 into 1. 3 should be greater than 2 into 1. So 3 is greater than 2. So obviously that condition is also satisfied. So we are basically going to hold that as one of our reverse pairs. So now next up, you can see this 3 is also present over here. So 3, 1 also makes a reverse pair. So there are a total of 2 reverse pairs in this array, none other than this. So the output is 2. So we'll basically have to detect the total number of reverse pairs that are present in the array with these two conditions. So now let's go to the approach. So okay. So let's see this example over here, that is 1, 3, 2, 3, 1. We'll work on with this example itself. So let's create this array over here, 1, 3, 2, 3, 1. So what is the most basic approach that will come to anyone's mind? The brute force approach, as you call it. So that will basically be that you hold one element. Okay, you take one, you start from the left, traversing from the left, you hold one value of I as 0, suppose, and you you just traverse all the elements, all the indexes that are on the right of I, and you take like you basically traverse them as j, like you take every index as j and you check for the two conditions. So I less than j. So if you're traversing on the right, obviously this condition is always satisfied. So now the only condition that you have to check is basically if array of I is greater than double of array of j. So you'll have to check this for all the elements that are present on the right of the ith index. So this you'll have to do for each and every element. You go to that element, you traverse on the right side of it to find any element that satisfied this condition. Okay, so you're basically doing this. Now can you imagine that traversing, like you hold on to one element and then you traverse to the right side, like the whole array on the right side of that element, that will take essentially O of n time, right? Because you're essentially like on an average, you're basically traversing the whole array itself. So now when you combine these both, you'll also have to hold on to every element as I, right, and traverse to the right. So it's essentially, when you calculate the total complexity, so there are two operations of O of n. One is for that you're holding every element as ith index, and then you're traversing on the right for the whole index. So if you combine those two, the effective time complexity is in the order of O of n square. Now like for questions like this, an order of O of n square is not really recommended. Like, so we will need to reduce it. So that's when our optimal solution comes in. So like cutting on to the point, many of you would be knowing about the concept of merge sort, right? You must have done the concept of merge sort. It's a basic sorting algorithm. I won't say it's very basic, but it's like something that everyone should know if you know about searching and sorting in arrays. So we'll be using an implementation of merge sort over here in order to count the inversions present in this array. Okay, now let's erase all this. So now what we're going to do is that, first of all, we are basically going to see that what the merge sort actually does. So merge sort has an effective complexity of O of n log n, in the order of n log n, and I'll exactly tell you how. So what merge sort does is that merge sort will, first of all, like suppose you have two pointers in merge sort, okay? You have one left pointer and you have one right pointer, or you can consider that as low or high, okay? So like suppose they're low or high, and then you have the low one is 0 and the high one as what is this, 4, okay, initially. So what we basically do is that we divide this array into halves, into two halves, okay? Let's divide this into these two halves, okay? Now you can put the middle element in any of the sides if you want to. You can put 2 here or 2 here, that doesn't matter actually. So this is how we did it, okay? Now again, okay, suppose again we divide this into two halves. So by default we are considering the middle element in this left half, suppose. So we divided this into two halves, okay, done. So now what we do is that again we divide this into two halves again. So this becomes 1 and this becomes 3, right? So we went to the roots, like we basically went until and unless those elements became like singular elements, okay? So now what we're going to do is that this is the last stage, we can't divide it anymore, right? So we basically now start doing our main operation, that is merging. Now we divided, okay, now we divided this array into halves like this. Now we'll be merging these, okay? Now what the condition that we'll be checking before merging is that is 1 less than 3. Yes, 1 is less than 3. So it will basically stay in its original order. Now just for example, I'm saying just for example, suppose this would have been 3 1 instead of 1 3. Suppose here it would have been 3 and then 1 2 3 1 3 1 2 3 1. So in this case, this here would have been 3 1, and here there would have been 3, here there would have been 1. If this would have been the case, in this case, actually you can see that here we'll be also performing the division, and here 3 is 1. Okay, fine. So I'll explain it with this only. I'll not mess you up with this. I'll explain it with this. So here it's 3. It's divided into 3 and 1, right? So here it's already this pointer, this left pointer is basically the value is less than the right pointer. So we basically continue with this combination itself. But here the left pointer value is basically greater than the right pointer value. Now this won't work. Why? Because we need to sort this array. Okay, I forgot to tell you one thing. We are by default sorting this in non-decreasing order. Okay, this merge sort example that I'm explaining is for sorting the array into non-decreasing format. So since if this element is greater, so we know that we need to like convert this into a non-decreasing format, so we need to turn this into less than. So what we do is we simply swap these both values. So this becomes 1 and this becomes 3. Done. So now we backtrack. Now this is our termination. We swapped also. Now we backtrack. So this became 1 3, right? Because we have swapped the value. So this has become 1 3 right now. Okay. So this part is 1 3 right now. Now this over here stays 1 3 because it was not swapped, because it was already less than. So now see, now our main part comes in. Okay. Now this is 1 3 and this is 2. Now our main merging, the essential merging algorithm comes in. Now what happens when we you must have also studied the question that is merge two sorted arrays. I'm assuming that if you are doing this question, you must have gone through this question, that is merge to sorted. If you have not gone through this question, you should just go. This is a medium level question. This question that we're doing right now is a hard level, but this is a medium level question. So you should just go and try this out once if you have not done this already. So here we are going to be following the same concept of merging two sorted arrays. So what we are going to do is, like suppose like just for example I'm telling, suppose we take this total, okay, this 1 3 2, this total length of one temporary array. Okay, so what we do is we start one pointer from this array. Suppose we're taking p1 at the start of this array, and this is just I'm not by array when I'm saying, I mean the part. Okay, don't consider it as a different, that we're breaking it into different arrays at every level. We're just dividing it into parts, just based on indexes. Maybe we'll see that later when we implement the code. So suppose we take the p1 pointer here at this index and p2 pointer here. Okay, so now what we do is, now suppose we take we have this temporary array over here for storing all these three values in sorted order. Okay, so what we do is, first of all, we check if array, suppose this this is array of p1, we check if it is greater than array of p2. Okay, if it is greater than array of p2, we know that we have to convert this into less than, right? As we have already seen in this condition over here, that if, this condition, sorry, that if at any point in this whole process, if we encounter any such pair, okay, any such pair of indices where this greater than like the index is on the left of the second index and the greater than relation occurs between them, we always have to swap that, and we have to convert that into less than. Okay, so here what we're going to do, we are not going to swap, but we are just going to store it, that like we are going to store this second element over here in temp. But here, as you can see, that array of p1 is basically less than array of p2, right? So we are just going to do nothing. We are just going to store this p1 value over here, because this is the less value, right? So if we are going to store our final sorted array in non-decreasing order, so we need to store the lesser value first, right? So if array of p1 is less than array of p2, we will obviously store array this array itself, right? So we like this p1 only, right? So we just do this, and we forward p1 from this to here, okay, from 1 to 3 to this index. Now see, now array of p1 is actually greater than array of p2. Okay, if it is greater, I have told you, if it is greater, we have to inverse it, we have to swap, like we have to basically make it less than. So now what we do is, now we don't carry the element of p1 into temp, we carry the element of p2 into temp. So we put this over here too. And then what we do is, now we see that this p1 only one element is left, so we put the remaining element over here. So you can see that this is basically forming a finally sorted array, right? Like we gave it two like different sorted sections, and it made that into one total like one full length sorted sequence. So that is what the magic of this merging algorithm is. Okay, so now this process, now this got converted from 132 into 123. Okay, fine. So now what we have to do is, now we have two sorted arrays again, here 1 3 and here 1 2 3. Now the same thing we will do, we will put one p1 over here, we'll put one p2 over here. Okay, now as you can see, we'll create again one temp array. Now the temp array's length will be 1 2 3 4 5. Okay, here, so 1 2 3 4. So this is the temp array for this stage. Now here what we're doing is, we're checking if array of p1 is less than array of p2, less than equal to. Okay, so fine, that equal to also we can consider. So here 1 is less than equal to 1. So okay, if we put this 1 over here and we forward this over here, okay, we p1 we forward it. Now what we do is, now 2 is greater than 1, right? So now it comes to this condition, that this is array of p1 is greater than array of p2, so we need to change it. So now what we do is, we copy the value of p2 here. So we copied 1 over here and we advance p2 to the next index. Now we see again that if array of p1, that is 2, is it greater than 3? No, it's less than 3. So obviously we will put the value of p1 first. So we put 2 over here. Okay, and we forward p1. So p1 comes over here on 3. Now is 3 less than equal to 3? Perfect. So we put the p1 over here. Okay, and p1 reaches its end, and only p2, like here in the second section, only one element is left, so we just put it off over here. So the final sorted array over here is 1 1 2 3 3. So this array will finally get converted into the final sorted array using this merge sort algorithm. So as you must have seen, that this was basically our total merge sort algorithm, and at every stage we are basically dividing it into like two sections. Now at every stage of the section that we are making, we divided this whole array into two sections first, then we again divided that like both the sections into two of its other sections. So this way, this whole dividing process will take a time complexity of O of log n, order of log n. Okay, and this merging thing, okay, this merging that is happening all around, like this merging, that merging, so it all of these merging techniques will effectively take a time complexity of O of n order. So when these both things are combined, so the total effective, that is the total effective time complexity taken by merge sort algorithm is O of n log n. Okay, So the total time complexity, effective time complexity taken, is O of n log n. Okay, so this is our merge sort algorithm. Now how will we implement our merge sort algorithm for doing this specific question, that is reverse pairs? Okay, fine. So I will be erasing all of this over here. So what was our array again? It was 1 3 2 3 1, right? So we will write down our array here, 1 3 2 3 1. Okay, so now in this question we have to basically find, I'll write down those two conditions again. I is less than j and array I should be greater than 2 into array of j. Okay, so we have to find all such ijk pairs. Okay, ij pairs, we have to find all such pairs. So what we are going to do is that we divide it in the same fashion. Okay, we just divide it in just like the same fashion that we did over there also in merge sort. So we did this 3 1 over here. Okay, so here the, you know what, the only difference that we're going to make is really simple. We are still going to merge merge sort this. The whole merge sort algorithm will still apply on this question too. We'll have to sort this. We're dividing this and we'll again have to sort this again, just like it happened in the merge sort algorithm. But in the meanwhile, in the middle, we'll also have to include one more step. Okay, remember when I told you that you will be given one, we'll have to take one P1 and then we'll have to take one P2. You remember that part, right? So what we do is that in the meanwhile, in the middle, when we merge these these two sorted arrays, like suppose this is already sorted 1 3 1 2. So when we merge these two arrays, okay, in the merging part, what we'll have to check is we'll have to insert this condition during the merging part. Okay, so we'll be checking if array of P1, okay, if it is greater than 2 into array of P2, because as you can see, P1, like P2 is starting from the second section, so it will always have to lie on the right side of P1. It will always be greater than P1. So that condition is already satisfied. That is I less than j, P1 less than P2. So here the only condition that else that we need to satisfy is that array of P1 is greater than 2 into array of P2. Okay, and this condition we will try to satisfy when we merge these both sections. So now as you can see that when we try to merge this, we will get into 1 2 3. Okay, 1 2 3. Sorry, one more section. So we will get the final array as 1 2 3. But as you can see here, no such pairs of P1 and P2 will exist, which satisfy this specific condition. So okay, we reach here. We have 1 2 3 over here. Okay, and as you can see, this will get swapped. So this will become 1 3. So we have 1 2 3 and 1 3 over here. Okay, perfect. So now what we're going to do is that we are going to put our P1 over here as usual. We're going to put our second pointer over here at the first index over here, 0th index. And what we're going to do is now we're going to try to again move and satisfy this condition. Okay, as you can see, there are basically here there is one point of P1. Like suppose if P1 is over here and suppose if P2 is over here. Okay, if P1 is over here and P2 is over here, so in this case we are going to see that this condition stays true, right? Because 3, if array P1 is 3, right, it is greater than 2 into 1. So yeah, this condition is true. So from here what we do is, suppose we have a count variable, okay, that is counting our reverse pairs. So we just do count plus plus if we find this condition over here. And also, okay, fine, we'll not do count plus plus. Okay, here it is very easy to see because there is only one element. We'll not essentially do count plus plus. We will do count plus equal to mid minus this P1 plus 1. Now I'll tell you exactly why we do this. Okay, mid minus P1 plus 1, why we do this. See, the thing is that suppose this is the mid, you know, right? When this array, when we divide it, we know that this is the middle element, so we are taking this as mid. Okay, so this 3 is mid over here, which lies in the first section. So suppose now just think of this, that here it would have been like this array over here. It's not 1 2 3. Suppose this is 1 3 5. Now you know that this array always has to be sorted, right? Because we have done all the swapping and all that before. So suppose this array would have been 1 3 5, just in case this array was 1 3 5 instead of 1 2 3, and this array over here is 1 3 as usual. Now see, this, when P1 will be on this 3, this will form a reverse pair with this 1, right? Because it obviously satisfied with this condition that 3 is greater than 2 into 1. Also, if you can see, every element that will be greater than 3, will also satisfy the condition, right? Because if 3 is greater than 2 into 1, so any number greater than 3, that is 5, like we can start from 4, 5, 6, 7, everything is going to be greater than 2 into 1, right? Every single element, that is every single number that is greater than this 3. So we know that this is our sorted array. This section is totally sorted, and every element that lies on the right side of this 3 will be like more than 3, right? And we know that all of them will form an reverse pair with this element over here. So what we can do is, we are simply doing CNT plus equal to this mid. Suppose this mid is at 5, okay? Our middle element is 5. Just think of it. So what we're doing is, we're doing count plus equal to mid minus P1. That is, mid is this, so we have plus 1. So we have here 2 elements, right? Because see, 3 1 forms a reverse pair, and again 5 1 will also form a reverse pair. So in total there are 2 elements over here, including 3, that will form reverse pair with 1. So we did this. Again, when we go to 5 will again form a reverse pair with 1. Okay, so you know that again gets added, so plus 1. So in total it is 3. So just like that, okay, just like that, we are simply going to be doing this. Now if you have done the questions, I'd like to point this out, that if you've not done the questions called count inversions, okay, I urge you to go and at least like watch any video regarding that once, because this count inversions question is really important if you want to understand this question. Like, if you have clarity on this count inversions, this is just a very slight modifications of the just one step ahead of the count inversions question. So if you have not done that, just to go do that, you will have a lot of clarity with this question too. So okay, fine. So now we understood that how we are counting these reverse pairs over here, okay? So now what we are going to do is, we are simply going to check that how we can implement all this in terms of code, okay? So okay, let's go to the IDE. So this over here. So first of all, as I told you that we'll be using merge sort, okay? So first of all, I'll tell you that how exactly do you use merge sort. If you've not watched any merge sort video or any tutorial, I would very much urge you to go and see that once, because you know that is a very like essential form of sorting method that you should always know. So it will essentially be like, we will have one merge sort function, okay? So I will have one like 2 indexes over here that will basically mark the starting and ending. This I and J, they will basically mark the starting, as I was telling you, low and high or left and right. No, so this is this will I and J will basically mark the starting and the ending index of every section that we're going to pass into this function, okay? So like this will basically help us dividing the array, like dividing that array into specific sections and then sorting them accordingly. So we are going to be doing this, and then we're going to pass the array, obviously, and also we are going to be pass that we're going to be passing that temporary array, as I told you, one temporary array. I'll explain you the functions of each and every data structure that we're using later, like why you're using those data structures. So okay, fine. So first of all, what we do is like we basically take one counter, that is reverse counter, okay? So first of all, we apply this recursive step over here. Now if you've not watched merge sort, I'll just like urge you to go and see that once, because otherwise this whole concept would not be very clear to you. So here we'll basically be doing I plus j by 2, and just to avoid the overflow, we are going to be writing that in a more fashionable way, that is I plus j minus 1 by 2, and by 2 you can write it as this right shift 1, that does the same function. So ref c plus equal to merge sort. First section that we're going to pass is from I to mid. I is basically the starting point. Initially we're going to pass it at 0. So 0 to mid, and then mid to 1. Once we called it from 0 to mid, like I to mid. So we put the temp and nums over here, and then next time we make one more recursive call. Okay, that is this mid plus 1. Now we covered the section from I to mid. Now we're going to move from mid plus 1 to j. That is, j is our higher, the end of the section that we're passing to this merge sort function. So we are going to be doing this, and the last thing that we're going to do is merging. We also have to have a function that merges both the sections, right, in a sorted fashion. So we're going to be passing this I, mid, j, temp and nums. Perfect. And ultimately we're going to return the maximum, the total reverse count that we have gathered. So now let's write the merge function, okay, that merges both the sorted sections of the array. So here we'll be taking the starting, mid and the ending of the section of the array. We're going to be taking the temporary array. We're going to be taking the array that is given to us. Okay. So I'd also like to point out this in this merge sort function, we're also going to be writing a base case, that is I greater than equal to j, because if the starting of the array itself is greater than equal to the ending of the array, then obviously it will not return any reverse count. It will just terminate. This is the base case in recursion basically. If you don't know that, you can watch any recursion videos. So fine. So this is the merge function. So initially what we do is we take 3 variables. Okay, like suppose I'll to make it simple, I'll just take it as p1 and p2 itself. So p1 we take as 1, okay, and so p2, what we have, p2 will be basically taking as mid plus 1, because obviously you know, right, that one section, I'd like to show you this, that one section is from this so suppose this is the p1, okay, so one section is from p1 to mid, and one section will be from mid plus 1 to p2. Sorry, not p2, mid plus 1 to j, like I to mid, it's not p1, sorry, I to mid, and one section is from mid plus 1 to j. Okay, so these are the two sections that we have divided the whole array into. So here what we're simply going to do is we're going to do this, and for the sake of marking the third array, like the temporary array in which we are going to store all the elements in the fashion like sorted fashion, we are going to be taking this p3 pointer. Okay, so okay, done. So now first of all we'll be counting all the reverse pairs. Okay, so we start writing the code for counting the reverse pairs, and what we do is we're basically going to be running a loop which will be basically from p1 to mid, that is from I to mid, that is in the first section, and also at the same time we'll also be checking for the second pointer, that is from mid plus 1 to high, okay, that is j. So we are going to be doing this. Now simply what we're going to be doing is we're going to be we're going to be cutting it short. We're simply going to be checking for the reverse pairs. Okay, so if nums of p1 is greater than 2 into nums of p2. Now I'd like to point one thing out, that multiplying with 2, now suppose it's now as you can see the constraints over here, it's like your this number can basically range from negative, the int min, this is basically the most least value of that an integer can hold, and can range up to the most, that maximum value that an integer can hold. So if it's 2 into something like this, so it will obviously overflow, right? The integer will overflow. So what we simply need to do is we need to convert into a long. Okay, so the range of long is obviously greater than this, so we simply do this, and for the sake of comparing it, we are just converting both into long. Okay, so now what we do is that if this condition for our reverse pairs, if this exists, we're simply going to be taking a reverse count over here too, and here what we're going to do is, as we discussed in our approach, we're going to do reverse count plus equal to the mid plus 1 minus this p1 right here. That's all that we're going to do over here. Okay, and at the same time we are also we moved our p1 array over there, like our p1 pointer over there, so the same thing we're going to do over here also. So here if this condition is not holding basically, so sorry, I think I just missed it over here. Here we don't do p1, we increased p2. If this condition doesn't hold, that means that we simply have to increase p1 here. Okay, so this is how we counted the reverse pairs. Okay, now after counting the reverse pairs, as I said, that the merge sort algorithm will totally appear in this question too. So we'll have to merge the array, so that in every such sorted while combining two sorted arrays, we can count this number of reverse pairs. In order to do that, we'll merge we'll also have to merge the array, two sorted arrays at every step. So now we are going to basically come into the merging part. Okay, merging into a single sorted array. So what we're going to do is we're going to reinitialize p1 to I. Okay, did we change the value of p2? Yeah, we also changed the value of p2, so we're going to reinitialize p2 to mid plus 1 as they were just before. So the way I initialize this over here, the same thing I'm going to do. So we didn't change the value of p3, so I'm not going to change the value of p3. So it's the same condition over here. Okay, if p1 less than equal to mid and p2 less than equal to j. Okay, done. This is done. So now just simply here we had checked for reversing the reverse pairs condition, right? Here we are going to simply check the condition for merge sort, the basic merge sort algorithm that is present. Sorry, I wrote this p1 and p2, it should be right. So this is the step. If this happens, we simply forward a p2, and if it's in normal order, we simply forward a p1. But here, as you can see, that we have also taken an we have to store this sorted fashion element in one other array. We're going to be using this temp array for the same. So we are basically going to be storing this over here. Okay, the element at p2 we're going to be storing at p3, and we're going to forward both p3 and p2. So this is going to be storing all the elements in a sorted fashion. Okay, this is just the way that I've explained earlier in this on the whiteboard, on the blackboard. So this is basically the same, essentially the same thing. So we did this. Now we are checking that if in any of these sections, now this basically we have merged both these sections, but if it might be possible that in any of these sections there are some of the elements that are still left. So in that case, we're simply going to put all those elements also in the final array. Okay, if p1 is less than equal to mid, if p1 is less than equal to mid, then we are going to we're going to put all those left values in this first section to temp, and if p2 is less than equal to j, we're going to put all the leftover values in second section to temp. Okay, as simple as that. We did that. Now what we have to do is we have to copy. Now we have stored the sorted values in temp. Now we have to copy all those sorted values into the final array, right, to make it finally sorted. So what we do is we take this, we go from I to j. I and j where are the first and last index of the whole section that we had passed on to this function, right? So we'll go from I to j, and we will copy all those values. Nums of x is equal to temp of x. That's what we did, and we return the reverse count from here. Okay, fine, perfect. So this is all we did. Okay, this is all we did. We have merged also, we have counted the reverse pairs also, we have merged them also, we merged the array, and then we have returned the reverse count. So now writing the main function that had been given to us, we are basically going to return this. First of all, we'll have to make this temp array, right? We're going to be passing the reference to the temp array, and so that our space is saved. So we're going to be defining it as the same size of nums, because in that case we won't be having to deal with a lot of index playing. So we'll just simply store it at the index that it is. So we do this, and then we return this merge sort function 0, the last index of nums. Initially, as I told you, we're going to be passing on the full array, right, as one whole section. So we're going to be passing this, and we're going to be passing the temp array, and we're going to be passing the nums array. Okay, So let's see if it runs properly. So okay, so I think this is nums. It should be nums over here, right? Because yeah, it should be nums over here. I wrote array. So the whole crux of this merge sort algorithm basically lies in this merging part. Like this is where you play with all the So let's test it. Okay, so fine. So let's test it on other example cases. This is a problem with LeetCode that I'm facing recently. Like you can't run the code frequently. So fine, this is producing a right result. So let's submit it and check. Okay, so it's passed. So as you can see that in this code, we have essentially like, let's just break down the intuition behind like why did we choose this merge sort algorithm. The only crux of this of this question that lies in our merge sort algorithm is basically this step over here. Okay, this step right here. This is the most important step that we have. Okay, this is why we're using this merge sort algorithm. Just to like during the merge sort algorithm, when we have an option to merge both the arrays, right, both the sorted arrays. Now while doing that, we are reducing the time complexity significantly right here, because suppose you have one element, right? I would like to show you, I would like to go back to the blackboard. Suppose you have an element over here and you are basically traversing to the right side and you are checking all the other elements. Okay, now instead of that, in this merge sort algorithm, you just have to do nothing just during this merging, like nothing else, nothing very hi-fi is happening. Okay, just during the merging part of this sorting, you're basically checking for this reverse pairs, and if this reverse pairs exist, you don't again have to check for all the elements on the right. Do you imagine? If you find one reverse pair, then for this first pointer, if you find that this forms a reverse pair with this one over here, so you don't have to check like this. Sorry, not this is unsorted. This is a sorted one. So suppose this 2 is forming a reverse pair with this one. Suppose. In this case, like 3, let's take this 3 is forming a reverse pair with 1. So in this case, you don't really have to again check that for 5 or any element. Suppose this was 1 3 5 7 9 and it goes like to a very long section. Suppose you had that, you don't have to again and again check for each and every element that lies on the right side of 3, right? You know that all the elements that are greater than 3 will always be greater than always satisfy the condition of the reverse pairs with 1. If 3 satisfies the reverse pairs condition with 1, all the elements that are greater than 3 will also satisfy the reverse pairs condition with 1, as mentioned over here. So that is basically essentially the crux of this of using this algorithm over here, that we are reducing the complexity. Like we simply here we are not checking for all the elements that lie on the right side of this pointer 1, right, on the right side of 3. We are simply doing wherever we have our mid. Okay, in the first section, wherever we have our mid, we just do mid minus p1. So all the elements that lie between p1 and mid, inclusive of p1 and mid, are basically all of them will be forming a reverse pair with this 1. So we do that in like O of 1 operation, the same thing that we had to do in O of n. Like we have to search all the things, all the elements on the right. We do that in O of 1. And essentially, as this merge sort totally requires an O of NlogN time, so we are not doing anything very special over here. We here also effectively in this question also, since we are using the same algorithm, just one step we are adding, and it doesn't change the average time complexity. So it basically stays O of NlogN. So we reduced our time complexity from O of n square to time complexity of O of NlogN. That is significant. So here basically that is the crux of the algorithm. We first have to, like I showed you that how to write the merge sort. If you're not really clear with this merge sort algorithm writing, then you can just go and watch some tutorial based on that. And apart from that, this part is this line is the main crux of the whole program that we have written. So that's how it is. So I would urge you to do 2 problems if you have not already done them. First is count inversions, that is present on LeetCode, and the one more problem is basically the merge 2 sorted arrays, that is also present on LeetCode. So both of this you can do, and you can get a better clarity of this question. So this is basically like a cherry on top of those both questions. So that's all for this video. If you have enjoyed this video, you can like, and you can put your suggestions in the comments for the next upcoming videos. If you have any requests, I'll be ready to solve those questions for you. Thank you, and have a great time.